Hello, my name is Kevin Craig. This presentation is on the modeling of mechatronic systems. In particular, the solution of the mathematical model derived from the physical model of the physical system that is under investigation. The mathematical model consists of nonlinear differential equations. These nonlinear differential equations must be solved numerically. Rather than writing lines of code to solve these nonlinear differential equations, engineers today use graphical programming. The two main programs that we use for graphical programming are Simulink, which is part of MatLab from the MathWorks, and LabVIEW from National Instruments. The advantages of graphical programming are twofold. The first is that everyone can be involved in the programming to solve the nonlinear differential equations of motion, as the graphical programming involves the creation of a block diagram, a graphical block diagram, and not writing lines of code, which very few people are expert in. So everyone participates in creating the block diagram, the graphical program, to solve the nonlinear differential equations of motion. And secondly, if the equations of motion involve some control code, which must be implemented in real time on the actual system, that control code can be autocode generated for a particular microcontroller that is part of the actual working system. So it is not necessary to take the control code and then write real-time code for a particular microcontroller, but that code can be autocode generated for any microcontroller that is used with the hardware system. So the benefits of graphical programming are huge, and it makes sense to spend some time introducing you to these two very important programs, Simulink and LabVIEW. Here are two block diagrams. On the top, a Simulink block diagram. Simulink is part of MatLab. On the bottom, a LabVIEW block diagram. They both look amazingly similar. They are both examples of graphical programming. Graphical programming either for modeling and analysis purposes or for the real-time implementation of control code on a microcontroller. The mechatronics engineer must be knowledgeable with both of these programs. Now we will examine Simulink and learn how to use Simulink for modeling and analysis purposes. First, let's answer the question, what is a system? A system is an assemblage of components or elements intended to act together to accomplish an objective. The view of a system as a set of interconnected elements is what has been called the systems approach to problem solving. The behavior of a system is specified by its input-output relation, which is a description, usually mathematical, of how the output is affected by the input. There are two types of systems, static and dynamic. Engineering dynamic systems can be small scale and large scale. What is a block diagram? A block diagram of a system is a pictorial representation of the functions performed by each component and of the flow of signals. It describes a set of relationships that hold simultaneously. A block diagram contains information concerning dynamic behavior but it does not include any information on the physical construction of the system. Many dissimilar and unrelated systems can be represented by the same block diagram. And a block diagram of a given system is not unique. Let's examine the electropneumatic transducer, a system we have looked at before. Here is a picture of that transducer, and here is a schematic that shows that it is truly a multidisciplinary engineering system with mechanical, electrical, electromechanical, and fluid elements. The block diagram shows its operation. In response to an input voltage in the range of 3 to 15 volts, an output pressure is produced in the range of 3 to 15 psig. The way it operates is that a voltage is supplied from some voltage source. That voltage gets applied to a coil. In that coil, then a current flows. Because that current carrying coil is in the magnetic field of permanent magnets, an electromagnetic force in that coil results. That force is applied to a spring mass damper system. The spring consists of these two cantilever beams, which have compliant springiness and also have some damping characteristic. At the bottom of this rigid mass, that's part of the spring mass damper system, is a float device in some viscous fluid that acts like a fluid damper. So the spring mass damper system consists of the two cantilever beams, this rigid rod and float, and the float inside this viscous liquid. As a result of that force, the mass moves, and we call this the flapper motion. This is the flapper at the end of this rigid rod. And the opening, the pneumatic opening, is then varied by the movement of the flapper. And this then results in some output pressure. Now, there are additional forces acting in our system. The pressure acts over the flapper area, and that force, pressure times area, acts opposite to the magnetic force acting on the spring mass damper system. Hence this summation junction with a plus and a minus for the two forces. In addition to the voltage that's supplied to the coil, as the coil moves in the magnetic field, Faraday's law tells us that there is a voltage, an electromagnetic force, an EMF voltage, called a back EMF, that results from the motion of the coil in the magnetic field. And that voltage is a speed-dependent voltage. So if XF is the flapper motion, taking the derivative gives me the flapper velocity. And this is the coil circuit voltage generator effect. So a voltage gets induced as I move that coil, that conducting coil, in the magnetic field. And Lenz's law tells me that the voltage will be opposite, hence the minus sign, to the input voltage that causes the motion. So this block diagram in words tells me how this electropneumatic transducer, a multidisciplinary engineering system, works. Let's look at a larger scale engineering system, a temperature feedback control system. We see the schematic here, and we see the block diagram that describes its operation below. This is a temperature control system for some chemical process. I measure the actual temperature with a thermistor. We see that in the block diagram. This gives me the actual temperature of the process. The desired temperature is set with a variable resistor in the Wheatstone bridge. The voltage out of the Wheatstone bridge is what we call our error voltage in this case. It is then amplified and sent to an electronic controller, in this case implemented with op amps, resistors, and capacitors. That control voltage, E sub m, is sent to our electropneumatic transducer, which in this larger scale engineering system can be represented by a first order electrical dynamic system, and will not have all of the details that we saw on the previous slide describing this system. Because if this component has been properly designed and is properly used, then its behavior in a system like this can be modeled very, very simply. However, the details of that multidisciplinary system are most important to the engineer who designed and built that system. The output of the transducer is a pressure, which is applied to a steam control valve, which varies the opening of the valve, which then controls the temperature in our chemical process. So this is a much larger engineering system, and the electropneumatic transducer is an off-the-shelf item that can be modeled very, very simply as part of this larger system. What is Simulink? Well, we've already said it's graphical programming. It is an extension to MatLab that allows engineers to rapidly and accurately build computer models of dynamic physical systems using block diagram notation. Linear and nonlinear systems can be modeled, continuous time and discrete time components can be used, graphical animations are possible. Previously, a block diagram of the dynamic system mathematical model was created, and then the block diagram was translated into a programming language. In Simulink, the computer program is the block diagram. This is graphical programming. This eliminates the risk that the computer program may not accurately implement the block diagram. What is LabVIEW? LabVIEW stands for Laboratory Virtual Instrument Engineering Workbench. It is a system design, prototype, deploy platform for mechatronic systems. It is graphical programming language from National Instruments, NI. LabVIEW programs, called virtual instruments, or VIs, have front panels and block diagrams. The front panel is the user interface, and the block diagram contains the programming code. LabVIEW is graphical programming for data acquisition, system control, and industrial automation. How does LabVIEW differ from MatLab? MatLab, which stands for Matrix Laboratory, is a numerical computing environment developed by the MathWorks. In mechatronics, MatLab is used for modeling, analysis, and control design for dynamic physical systems. Simulink, which is part of MatLab, and LabVIEW, block diagrams, are very similar, and the steps to create block diagrams in either environment are the same. Why are Simulink and LabVIEW important? The potential productivity improvement and cost savings realized from the block diagram approach to programming is dramatic. There are two principal strategies for their employment. First, rapid prototyping. This is the application of productivity tools to develop working prototypes in the minimum amount of time. Here we optimize for development speed rather than execution speed or memory use. A hierarchy of physical models is used in this phase. Physical system design and control design are optimized simultaneously. Second, rapid application deployment. Here, the final computer program is the Simulink or LabVIEW model, or in the case of Simulink, is derived from the model through automatic C code generation. Here we see our familiar engineering system investigation process. And I've highlighted the blocks in the process that we will be focusing on: the physical system, the physical model with parameter identification, the mathematical model, and the mathematical analysis. Simulink uses the mathematical model represented in block diagram form and predicts the dynamic response. That is, it solves the equations of the physical model, not the actual physical system. We are predicting the behavior of our model, not the physical system. When we make measurements, we measure the actual physical system. As an example, consider the spring mass damper system you see in the photograph. The physical system consists of a base plate and a support to which I attach a real spring, and then a mass with a tray or various weights, essentially a rigid body, that's mounted on the side to a linear bearing. I measure the displacement of the mass as it goes through its up and down motion using an ultrasonic sensor. So I have a real spring, a real linear bearing, a real support, real mass, and I need now to create, using engineering judgment and simplifying assumptions, a physical model of this physical system. So the assumptions that I will make are that, one, the support, the base plate, the vertical support structure is rigid. As the system undergoes its motion, it does not flex. It is connected to ground, so all measurements made with respect to this support system are absolute, measured with respect to ground. While the spring is real, it has mass, it dissipates energy upon cycling, it has compliance, I will treat it as a pure and ideal spring. A pure spring means it only has the attributes for which it is named: springiness, compliance. Ideal means that it's linear in behavior. So although the spring has mass, I will neglect it. The spring dissipates energy, but I will neglect that. The spring is nonlinear. If I stretch it too much, I will treat it as being a linear spring, and I will stay within its linear range of operation. Neglecting the mass of the spring is appropriate. If the mass of the spring is much, much smaller than the mass attached to it, this is acceptable except in very high-speed applications. The motion of the spring will dissipate energy, but what I'll assume is that energy dissipation is negligible compared to other dissipation mechanisms, notably the linear bearing, which is the source of almost all of my energy dissipation. So this linear bearing will have a combination of fluid damping and Coulomb friction, dry friction damping, which is nonlinear. Initially, in my first model, I will neglect the nonlinear Coulomb friction damping and treat the damping as being just viscous, linear viscous friction. So I treat this linear bearing as a pure and ideal viscous damper. So pure means only has the attribute for which it is named, a viscous damper, has no mass, no compliance, and it's ideal. linear in behavior. So it'll be characterized by a single damping coefficient, which of course will have to be determined experimentally because there are no formula for friction coefficients for linear bearings. Because the linear bearing restricts the motion of the mass, confines it to simple up and down motion, prevents it from moving side to side, in and out, or twisting, I have essentially a 1 degree of freedom system, and it's in the x direction. Degree of freedom means how many coordinates, independent coordinates, are needed to completely describe the motion of the system at any time. In this case, I only need one, and I'll call that x, and I'll call positive down. Treat the mass as being rigid. It certainly is not deformable in this application. It's a rigid mass. Because it doesn't change its orientation as it goes through its motion, I can treat it as a point mass. The system is vertical, gravity acts down in the positive x direction. I've just assumed the positive direction to be down. As I mentioned, the actual motion of the mass is determined by an ultrasonic motion transducer, which will give me a voltage proportional to displacement of the mass. The next step is to draw a free body diagram of my mass. So I simply take this mass and I take it out of its environment and I draw it on my page. I will show all the forces acting on this mass. The forces that are possible are forces that act at a distance, electromagnetic forces, and gravity, weight, and forces of contact. No contact, no force. I have no electromagnetic forces. I do have weight. However, as we will see, I need to specify where I measure x from, and I have two choices. I can measure x from the unstretched length of the spring, in which case the weight force needs to be shown on the free body diagram, or if I measure x from the static equilibrium position, which you see it in here, with the spring statically stretched to offset the weight in a static position, I don't need to include the weight on my free body diagram as the weight is offset by the static stretch of the spring. So when we measure x from the static equilibrium position, I don't need to show the weight on my free body diagram. F of t simply represents any externally applied force that I might apply to my mass. The spring force and the damping force, these are due to my pure and ideal spring, pure and ideal damper. The spring force is proportional to the relative displacement of the ends of the spring. One end of the spring is connected to ground, the other to the mass. As the mass moves in the x direction, the spring gets stretched, the spring is in tension, the force acts up, equal to k times x. The damper, this pure and ideal viscous damper, the damping force is proportional to, with the coefficient b, proportional to the relative velocity of the ends of the damper. One end is connected to ground, the other end is connected to the mass. As the mass moves down with a positive velocity, the damping force will want to pull it back up, and that force is proportional to that velocity, b times v. So on my free body diagram, I've now shown all the forces acting on my mass. To get the mathematical model, I apply Newton's second law, which says the summation of these forces will equal mass times acceleration of this mass, the absolute acceleration, the acceleration measured with respect to ground. Summation of forces equals mass times acceleration. So mass times acceleration, with acceleration acting positive down, equals what forces? Minus b times v minus k times x plus f of t. If I rearrange the equation, I get mass times acceleration plus b times velocity plus k times displacement equals the externally applied force. If I now solve for the acceleration, I get the acceleration equals 1 over the mass times the sum of minus b times the velocity minus k times x plus f of t. This then becomes the mathematical model of my physical model based on simplifying assumptions, which is the model for this real physical system. Now let's draw the Simulink diagram for my mathematical model of my physical model. First, let's talk about inputs to a dynamic system. Engineers typically use two inputs to evaluate dynamic systems, a step input and a sinusoidal input. By a step input of any variable, we will always mean a situation where the system is at rest at time t equals 0, and we instantly change the input quantity from wherever it was just before t equals 0 by a given amount, either positive or negative, and then keep the input constant at this new value forever. This leads to a transient response called the step response of the system. When the input to the system is a sine wave, the steady state response of the system, that is, after all the transients have died away, is called the frequency response of the system. These two input types lead to the two views of dynamic system response, time response, and frequency response. Here is my Simulink block diagram. And this is for my mathematical model, which I show here at the bottom left corner. So as you see, I have solved for acceleration, which in terms of derivatives is the highest derivative in my equation. Acceleration is the derivative of velocity. Velocity is the derivative of position. So this is the highest derivative in this equation. I solve for that. And I note that A, the acceleration, is equal to the sum of three terms times a constant 1 over m. So my Simulink diagram starts off with the acceleration, as represented by this line. Now to get velocity, I must integrate. Now I don't integrate myself. I let Simulink integrate for me. It numerically integrates. 1 over s is the symbol in Simulink for integration. And I integrate with knowing the initial velocity at time t equals 0. If the system starts from rest, then that initial velocity is 0. To get position, I integrate velocity. Again, 1 over s. And that gives me position, where I have an initial position, initial condition in this integration block. So you can see that acceleration by integration leads to velocity with an initial condition on velocity. Velocity, integrating velocity leads to position with an initial condition on position. Once I build this, what I call is the stem, I then simply do what the equation tells me to do. It says acceleration is equal to 1 over m, and this block is a gain block. A gain block simply says take whatever comes in and multiply it by whatever's in the gain block. So acceleration equals 1 over m times this arrow. This arrow is the output of the sum of these three terms. This is a summation block. So what comes into the summation block will be f of t, which I will then put in as a step input, and I'll explain how we would implement that. And then I have minus b times v. Well, this arrow here represents velocity. So if I pick off velocity here, and I bring it into a gain block, multiply it by b, and then bring it back into my summing junction with a minus sign, I have minus b times v. This is position. If I pick off position here and bring it into a gain block, the gain block with a value k, I get k times position, and that goes in with a minus sign into my summation block. And so then this completes the block diagram. How do I know my block diagram is correct? Well, there is never any reason why your block diagram should be different from your equation of motion or equations of motion. The reason is because the last step in the whole process is to write the equation of motion from the block diagram. Now, the equation may be incorrect, but the block diagram should always be consistent with the equation. There's no reason for it not to be if you perform this step. So let me perform this step. Acceleration integrated once gives me velocity, integrated again gives me position. Acceleration equals 1 over m times the sum of my input force minus b times velocity minus k times position. And that's my equation of motion. This is a correct block diagram. I can send the output, either position or velocity or any signal, to the workspace for plotting or for analysis. And that's what this block does. To implement a step response, I simply would take a secondary mass, in this case the blue mass, and I would simply put it on the mass of my spring mass damper system. So in the actual physical system, I would just add another plate to that tray. And at time t equals 0, I would release it. And what I would see is that the spring mass system would oscillate, eventually then settle and assume some new equilibrium position. And this is what we call the step response. And this is the prediction of the step response from MatLab, Simulink. And I would compare this to the measured step response from my ultrasonic transducer, make that comparison, and then decide if my model is adequate or not. And if it's not, I then need to revisit my simplifying assumptions and make some modifications. In order to run the Simulink simulation that I presented on the previous slide, we need parameter values, in particular values for the mass, the viscous damping coefficient B, and the spring constant K. To determine the value of the mass M, I can simply weigh that mass. So that it's very easy to determine that parameter value. To determine the spring constant, I would take the spring and do 2 static tests with the spring. I would apply a known weight W1 to the spring and measure its displacement, its stretch. I would apply a second weight to it, W2, and I would measure its displacement or stretch. I would plot these two on a graph, these 2 data points on a graph, as I show here, and assuming linear behavior, draw a straight line through those 2 points. If the straight line does not intersect the vertical axis at the origin, then where it intersects the vertical axis indicates what we call pretension, that in order to get the spring to stretch, to get the coils to separate, I need to apply a certain initial force before the spring will start to stretch. This is called my pretension, F sub t. I'm assuming that I don't have a pretension in my system and that my curve, straight line curve, will go through the origin. And I assume that my curve is indeed straight line, that it's linear in behavior. If I were to stretch the spring perhaps more, this straight line would no longer be straight. It might be curved, indicating a stiffening spring or a softening spring. So that is how I would determine the slope of this force displacement curve, and the slope is my spring constant. Now, to determine the friction characteristic, in particular the viscous damping coefficient, is a little more involved. There are no formulas we can use for a linear bearing. And so I'd have to do some testing on that linear bearing. I know from previous experience, and we will also cover this in the future, that if I have a oscillatory system that has no damping, then the oscillations will persist and will not diminish at all, as indicated by this black curve. If I have viscous damping, then the oscillations will decay, as shown by the red curve. And if I looked at the envelope of these oscillations, looked at the peaks of these oscillations, the envelope of those oscillations is an exponential decaying curve. If I have pure Coulomb friction, nonlinear Coulomb friction, dry friction, then the oscillations will appear as they are here in blue. And the envelope for these oscillations, if I were to connect the peaks of these oscillations, that envelope would be a straight line. So if I have an envelope that is linear, I have Coulomb friction. If I have an envelope that is exponential decay, I have viscous friction. And most probably, my behavior will look something like this. It will be somewhere in between an exponential decay and a linear decay, in which case I have both Coulomb and viscous friction. So one way to determine what you have is to do some curve fitting and determine whether you have viscous friction or Coulomb friction or a combination of both and what those coefficients could be. So in this case, I want to determine a coefficient of friction B that best represents the actual behavior of the system, something that captures both the viscous behavior and the dry friction behavior. So this could be a little bit of work, but the parameter identification needs to be done. And the value that I would obtain for B, I would use in my Simulink simulation to predict the response. And then I would compare that response to the actual measured response. And based on that comparison, I could then make some decisions as to the effectiveness of my model or the effectiveness of my parameter identification. Here are some Simulink block diagram suggestions. Always sketch the block diagram by hand before creating the Simulink diagram. I certainly did that in this case. I didn't show it to you, but I did it. And the reason we do that is to show the complexity of the diagram, the blocks needed, and the arrangement of blocks, because careful arrangement of blocks and signal lines can make relationships easier to follow. If you try to create a Simulink diagram from scratch in Simulink for anything but the most simple systems, the diagram will look very, very cluttered or confusing, will not be organized, and the time you spend with a hand diagram will give you an idea of the blocks you need, the location of the blocks in the diagram, the location of annotations you might want to include, and so forth. Secondly, naming blocks and signal lines and adding annotations to the model can make the purpose of the model elements easier to understand. Your Simulink diagram must be understandable without you being there to explain it. This has to be usable by other engineers without you being there. So it has to stand alone by itself. So you need to annotate your diagram and have to have it be complete and thorough, self-explanatory. Lastly, the best way to ensure that your Simulink block diagram accurately represents your mathematical model equations is to write your mathematical model equations directly from the Simulink block diagram, and then compare your result to the actual equations. This won't cover any errors before you start to use your block diagram to investigate model behavior. So there's never any reason why your block diagram should not be consistent with the equations of motion. Why? Because you write the equations of motion from the block diagram. An error will be uncovered immediately. This doesn't mean that the equations of motion are correct. It simply means that your block diagram represents those equations of motion graphically. The two simplest mechanical dynamic systems are the 1 degree of freedom spring mass system and the 1 degree of freedom simple pendulum system. I can combine these two systems and create what we call the spring pendulum system by replacing the fixed connection of the spring to ground in the spring mass system with a revolute joint. The result is the spring pendulum dynamic system you see here. Here are two videos of the spring pendulum dynamic system. In the first video, the initial conditions, the radial displacement of the mass and the theta displacement of the mass, are such that I pull the mass straight down with essentially zero angular displacement, and I release it. What you will observe is a transference of energy from a spring mass motion to a simple pendulum motion, back and forth, that persists for quite a while as there is very low energy dissipation in the system. In the second video, the initial conditions are different. I give the mass a non-zero angular displacement, maybe 15 degrees, and then I release the tension in the spring somewhat so that then when I release the mass, the motion that results appears to be a simple superposition of spring mass motion and simple pendulum motion. Clearly, if the model we create, both physical model and mathematical model for the spring pendulum dynamic system, if it is to be useful, must be able to predict both motions in response to the two different sets of initial conditions. Let's look at the videos. I pull the mass straight down in video 1. It oscillates up and down and then starts to swing in simple pendulum motion. Then the simple pendulum motion reverts back to spring mass motion, up and down. This type of behavior is what we call nonlinear resonance, and is very common in satellites and ships. In the second video, I pull the mass off to the side, release some of the tension, and now you see it simply swings back and forth in what appears to be uncoupled spring mass motion and simple pendulum motion. So here is an introduction to the spring pendulum dynamic system, and I call it an interesting experiment. Take any spring and measure its unstretched length L. Attach a mass to the end of the spring. Choose a mass so that the equilibrium length of the spring, that is the length of the spring when there is no motion, is about 1.33 times L. Secure the upper end of the spring to a fixed point, a fixed pivot point. Pull the mass straight down a little bit from its equilibrium, release it, and watch its motion. We saw this in video 1. The mass moves up and down like a simple spring mass system should, but after a little while, the angle the spring makes with the vertical starts to increase, while the up and down, or in and out, motion decreases. It decreases until the spring swings laterally only, like a simple pendulum, essentially without in and out motion. Then the angle starts to decrease and the in and out motion starts to appear again. The sequence of events repeats itself. Why? Well, as I said, this is the spring pendulum physical system. There is a range of values for the mass for which this described phenomenon occurs. For values of mass outside that range, the motion takes place essentially along the vertical where it started. This is a nonlinear phenomenon called nonlinear resonance. It cannot be predicted by linearizing the differential equations of motion for small amplitudes of motion. This phenomenon occurs in many dynamical systems: satellites, ships, airplanes, buildings, and machines. And every engineer should be aware of it. The topics we will cover are the physical modeling of the spring pendulum system. That includes simplifying assumptions and parameter identification. The mathematical modeling of the physical model, and for that we only need particle dynamics, that is, particle kinematics and particle kinetics, something engineers learn in the first few weeks of a sophomore dynamics course, or even in elementary physics. And lastly, we'll predict the response using MatLab Simulink, as this is a nonlinear system and the equations of motion cannot be solved analytically, and we'll compare them to experimental measurements. Here is the engineering system investigation process, which you are very familiar with, and which we will be applying to our spring pendulum dynamic system in order to understand its behavior and to create a model that we can use for further investigation, a model that is validated by actual measurements. You always must compare the predictions of your mathematical model to actual measurements, because a computer simulation without experimental verification is at best questionable and at worst useless. What physical model simplifying assumptions will we make? Well, we will treat the spring as a pure spring. It only has the attribute for which it is named: spring, compliance. We will neglect its mass or inertia, and we will neglect any energy dissipation associated with its cycling. We will treat the spring as being ideal. That means linear in behavior. The pivot, the revolute joint, we will consider to be frictionless. We will neglect all material damping in the spring and any air damping in the system. Even though the mass at the end of the spring, as it goes through its motion, does not maintain its orientation, so the motion it is performing is really general plane motion as it is translating and rotating, we will neglect the rotational inertia of the mass. We will treat it as a point mass. This simplifies the equations of motion considerably, and we can always revisit our simplifying assumptions at the end when we compare our predictions to our measurements and try to understand any discrepancies. This is a 2 degree of freedom system. As the mass moves in and out in radial motion and left and right in theta motion. Polar coordinates are the natural coordinate system for the spring pendulum motion. R and theta are the coordinates we will use to describe the motion, and in doing so, we assume there's no out-of-plane motion. The mass moves in a plane, and the spring does not bend or flex other than the way it's supposed to flex by design. It doesn't bend. And lastly, the support structure is rigid. So the pivot point, the revolute joint, is fixed to ground. These are our simplifying assumptions, and our comparison of measurements with predictions will then verify whether these assumptions are valid and can be used for further analysis and further insight. These physical modeling assumptions lead to what we call the design model, one that gives us insight and understanding. And as we know, there's a whole hierarchy of models possible. The design model is the less real, less complex, more easily solved of all the possible models. If we wanted to make our model more real, more complex, less easily solved, the model assumptions that would lead to the truth model might be include pivot friction, which could be a combination of viscous friction and Coulomb friction. Treat the spring as not pure, that it has mass or inertia, and it also has energy dissipation. Treat the attached mass as a rigid body, and not a point mass, and this will add a degree of freedom to the dynamic system. Here is our physical model with physical parameters that have been identified, and we will discuss how these values were obtained. Our physical model consists of a revolute joint that is frictionless and fixed to ground, a pure and ideal spring of unstretched length L attached to a point mass. The motion is 2 degrees of freedom. All the motion takes place in the plane of the paper. The coordinates used to describe the motion are motion in the radial direction, the plus r direction, and motion in the theta direction, the plus theta direction. So we're using polar coordinates, r and theta, to describe the motion of the spring pendulum system, as these are the natural coordinates for this system. The parameters that we need to identify are the pendulum mass, which we weighed, the spring mass, which we weighed, the unstretched length of the spring, which we measured, the spring constant, which we had to perform 2 tests, static tests, to determine the value of. The acceleration due to gravity, we assume is constant and given. The pretension of the spring is something we discover in our test to determine the spring constant. The static stretch of the spring can be measured. This is the stretch of the spring when the mass is in static equilibrium. The mass is not moving, and the spring static stretch simply supports the weight of the mass in static equilibrium. The dynamic stretch of the spring is the stretch of the spring beyond the static stretch of the spring. And of course, the total stretch of the spring is the static plus the dynamic spring stretches. In order to determine the spring constant and the pretension in the spring, we perform 2 simple experiments. We hang a weight from the spring and note its displacement. We hang a second weight from the spring and note its displacement. We assume linear behavior, straight line behavior, and we draw a straight line connecting those 2 points. The slope of the line is our spring constant. The intersection of the line with the vertical weight axis is our pretension. I show the results of that test here. The spring constant is measured to be 172.8 newtons per meter. It intersects the force axis, the spring force axis, at 5.71 newtons, which is the spring pretension. And when the mass is hanging from the spring displacement is 0.070 meters, which is the static stretch of the spring. And the spring force at that static stretch supports the weight, mg, 17.805 newtons. So according to our engineering system investigation process, we've made simplifying assumptions guided by engineering judgment to obtain a physical model of our spring pendulum dynamic system. We've identified the parameters in that physical model. We now apply the laws of nature to our physical model to create the mathematical model. The law of nature that we will use here is Newton's second law for a particle in plane motion. And it says that the summation of the forces acting on the particle will equal the mass times the vector acceleration of the particle. So this is plane motion, and the particle moves with 2 degrees of freedom. We have identified those 2 degrees of freedom as the r direction and the theta direction. So our equation of motion then, which is a vector equation, becomes 2 scalar equations. It simply says the summation of forces in the r direction will equal the mass times the absolute acceleration of the mass in the r direction. That's the acceleration with respect to ground. And then the summation of forces in the theta direction will equal the mass times the absolute acceleration of the mass in the theta direction. That's the acceleration with respect to ground. So the summation of forces in the r direction is simply mg times the cosine of this angle theta in the positive r direction. And in the negative r direction, we have k times r, which is the total stretch of the spring, static plus dynamic, plus the pretension. And the sum of those 2 forces must then equal the mass times the absolute radial acceleration of the particle. The summation of forces in the theta direction is simply the theta component of the weight, or minus mg sine of theta. And that's the component of the weight in the negative theta direction. There are no spring force components in the theta direction. And that must equal the mass times the absolute acceleration in the theta direction. So what is the absolute acceleration in the r direction for a particle in plane motion using polar coordinates? And what is the absolute acceleration in the theta direction for a particle in plane motion using polar coordinates? Well, it's something we could derive, but it's also something you could look up in your dynamics textbook. So basically, there are 4 components to our total acceleration. In the radial direction, we have what is called radial acceleration, which is the second derivative of r with respect to time. And then we have what is called the centripetal acceleration, which is in the minus direction, and it's equal to L plus r times the derivative of theta with respect to time squared. This is the centripetal acceleration. In the theta direction, we have what is called tangential acceleration. This is L plus r times the second derivative of theta with respect to time, plus 2 times 2 derivatives, the first derivatives of r and theta with respect to time. And this is what we call Coriolis acceleration. So we don't need to know what physically these represent, and we don't need to derive these at this time in order to use these in our mathematical model. We just have to make sure that the formulas we use from references like a dynamics textbook are defined properly in the same geometry and the same parameters that we use in our free body diagram. So if I put all this together, I get these two equations of motion, which are nonlinear. Why? Because we have the squares, square of theta dot. We have the product of derivatives. We have a dependent variable times the square of theta dot. We have a cosine. We have a sine. These are all nonlinear terms. These two equations, they are coupled, as I have r and theta and their derivatives in both equations, cannot be solved analytically. And so, since they can't be solved analytically, I must use Simulink to solve them numerically. So here are our nonlinear equations of motion. On the left, we have the summation of forces in the r direction equals mass times the absolute acceleration of the particle m in the r direction. On the left, the summation of forces in the theta direction. On the right, the mass times the absolute acceleration of the particle m in the theta direction. And so what remains is to build a Simulink block diagram to solve these two equations. Now that we have our nonlinear equations of motion, let's create the Simulink block diagram to solve these equations numerically, as they cannot be solved analytically. There are 4 steps to create the Simulink block diagram that represents our equations of motion. And these 4 steps apply whether we have 1 equation or 20 equations. The first step is in each equation, solve for the highest derivative. In our first equation, the highest derivative is the second derivative of r with respect to time, r double dot. We solve for it using algebra. We see that result here. In the second equation, the highest derivative is the second derivative with respect to time of theta, theta double dot. Using algebra, I solve for it. We see that result here. If, for example, each of these equations had both r double dot and theta double dot in both equations, then by algebra, we would have to recombine these equations so that each equation only had one of the highest derivatives. And then we would proceed with the following 4 steps. So now I've solved for the highest derivative in each equation, r double dot, theta double dot, and I have what each of them equals. Step 2 is to create for each equation what I call a stem. To go from theta double dot to theta dot, I integrate with an initial condition on theta dot. To go from theta dot to theta, I integrate with an initial condition on theta. That's one stem. To go from r double dot to r dot, I integrate with an initial condition on r dot. To go from r dot to r, I integrate with an initial condition on r. This is step 2. If you have 1 equation, you'll have 1 stem. 20 equations, 20 stems. Step 3 is do what the equations say. So now let us use MatLab Simulink and create the block diagram that says in block diagram form what the equations say. So now I will implement step 3, which is building the block diagram in Simulink. Now I've posted a video of me creating the block diagram in MatLab Simulink live. So the video shows me building the block diagram live in MATLAB, performing all of the steps in the MATLAB Simulink environment. Please use that as a supplement to what I will do here, which is describing the same process in a shorter way using screenshots. So please take advantage of both ways that I presented this step. Here you see I've opened up MatLab. I prefer to just have the command window open. And once I'm in the command window, I see on the toolbar Simulink, and I pick Simulink to open up the Simulink space, the blank document that I will draw my block diagram in, along with the library. Now, for this, I'm using MATLAB 2015. In the video, I use MATLAB 2017. Nothing much changes or has changed with Simulink over the past 10 years in terms of how we create block diagrams. Some additional blocks have been added to the library. There have been cosmetic changes, but the basic process is the same. Also, when you create your block diagram in a lower version, meaning an earlier version, you can run it in later versions of Simulink. So for example, the version in 2017 can be run easily in 2018 or 2019, but could not be run in a version earlier. Similarly, if you create a block diagram using the latest software from MATLAB, you can't run that in an earlier version. You could save it so that it can run in an earlier version, but you just have to take that additional step. Okay. So now my Simulink library is open. This is my library browser. And so in this version, I'll go to this icon and I'll select New Model. And so now I have, this is my white space. This is my blank sheet of paper. This is where I will build the Simulink diagram. And I will first build the two stems, and then I will do what the equations say. And you should save your model as you create it. And I'll save my model, name it Spring Pendulum Dynamic System. MATLAB will not allow you to have spaces in any of the files that you name, so you must use this underscore. And that's the file name, and you save it in a directory that is convenient for you. So once I do that, I have my file name, it shows here, and here is my blank sheet of paper in which I will create first my two stems, and then doing what the equations say, the block diagram. While I have not shown my hand-drawn block diagram, I have done that to know which blocks I will need, and also to get a good understanding of the complexity of the diagram and how I might lay it out. This is something that's important for you to do. It doesn't take much time. It will save you a lot of time in Simulink in building your block diagram. So I know the blocks I need for my block diagram are from the continuous library. I need an integrator. From the math operations library, I will need a gain block, a math function block, a product block, a trigonometric function block, and a summing block. From the sinks library, I will need a scope, a two workspace block, and an XY graph block. From my sources library, I will need a constant block. So a word about Simulink block diagram manipulations. You left click, hold, drag and drop to bring a block from the Simulink library to the model workspace. You left double click anywhere on the model workspace and start typing to add annotations. You right single click on a block, hold and move away to duplicate it. You left single click on the output port of a block, hold and move to the input port of another block to connect two blocks. You right single click on a line and hold to branch off to connect to another block. You can right single click on any block to change its appearance and format, and you can left double click on any block to set its parameters and functions. Now I write all of these instructions down. In the video, you'll actually see me doing this as I'm building the MatLab Simulink block diagram live. So I've dragged into my workspace the blocks that I will need. These are all the blocks that I will need for the spring pendulum system. And we know this because we created the block diagram for the equations of motion on paper by hand before we even turn the computer on. We know the block diagram is correct because we can write the equations of motion from the block diagram. And so I go to diagram, format, font style to enlarge the font. Usually the font that is the default is rather small, so I like to enlarge the font, make it easier to see, certainly easier to present. So here I've just enlarged the font. I can also grab the corners of the blocks and resize them. Again, in the video, you'll see me actually doing this. So I make the blocks a little bit bigger. Now I create my two stems. So I have my integrator block, which I connect to another integrator. The input to this will be theta double dot. This arrow, this line, this signal is theta dot, and the output here will be theta. Similarly, I have an integrator that will integrate R double dot to give me R dot, and this integrator will give me R from R dot. So I've created my two stems and I've added some annotations. And at the bottom, you see the rest of the blocks that I will be using. Now I've completed the block diagram here, so I've taken a lot of work. I don't show you, but in the video, I show you how I do this step by step. So the key here is that this block diagram that I've created, I should be able to write the equations of motion from the block diagram. And there is no reason why every block diagram should not be consistent with the equations of motion. So let me show you how we would do that. This is theta double dot, which I integrate once to get theta dot, and I integrate again to get theta. So theta double dot equals the product of what? The product of, and I follow this arrow around, and I follow it to here, the product of 1 over the sum of L plus R. So this is L plus R, 1 over L plus R, and it's multiplied by this summing block. The summing block has the summation of minus what? Minus the product of G and the sine of theta, minus 2 times the product of theta dot and R dot. And that is the correct for one of the equations of motion, the theta double dot equation. Now if I look at the R double dot equation, R double dot integrated once gives me R dot, integrated again gives me R. R double dot equals the sum of 4 terms. So plus, and I follow this around, plus the product of G and the cosine of theta minus the product of K over M times R plus the product of the square of theta dot squared and the value of L plus R, that sum, which comes in here. And it's the product of those two that comes in with a plus sign. And lastly, I have minus Ft over M. That is then my R double dot equation. Note here that for each integrator, there has to be an initial condition on theta dot, R dot, theta, and R. For theta dot and R dot, the initial condition is 0. The system starts with 0 velocity in the R direction, 0 velocity in the theta direction. The initial conditions are on theta and R, and depending on which of the videos you want to do a simulation of, they each have two different sets of initial conditions. The blocks on the right here, this is an XY graph block. This is a scope block. This just simply multiplies one of the inputs into the XY graph with a minus sign, so it gives me the representation that I desire. These two blocks are two workspace blocks, and here's another scope block. And you can change the labels on these blocks. You can also hide the labels, and you can add color to the blocks and color to the signal lines. So you can make this as easy to understand as you wish. And much of that is covered in the video. So please, when you want to build this block diagram, and you should build a block diagram yourself from scratch, you should do it with the help of the video to do that. This just guides you and gives you the steps in the process. The video is meant to give you the details of how to actually do this. So some guidelines. Never put numbers into the Simulink block diagram unless the number is part of the actual equation. We have a term in this equation that's 2R dot theta dot. That number 2 can be put into the Simulink diagram because that will not change. But you should always use variables, even for initial conditions. Define the variable values in the workspace or create an M file with the parameter values defined. Simulink, when it comes upon a variable, will look to the workspace to find the value of the parameter. And if it doesn't find the value of the parameter, you'll get an error. So, but you never want to put the values of the parameters in Simulink. So for example, if the mass M variable appeared in 5 equations in your Simulink block diagram, or in 5 different places, and you wanted to change it, if you put in the value in your Simulink diagram, you would have to change it in 5 different places. If instead you just have the variable M and you want to change its value, you just have to change it in the workspace, change the value, and Simulink will read that value and then assign it to M wherever it appears in the block diagram. So here is an M file, which is just a file that shows the values, in this case of our parameters. You see the value of M, G, K, pretension, unstretched length of the spring, initial condition on theta, initial condition on R. And in an M file, if we have a percent sign, everything after the percent sign is a comment and is not read. It's just for ease of understanding what's in the M file. So as you can see, this is my spring pendulum dynamic system parameters. Here are the parameters. I specify what they are as well as the units associated with them, because MATLAB Simulink does not keep track of units. If you mix units, well then MATLAB and Simulink will not pick up the error and your answers will be incorrect. So to run this simulation, in this version of MATLAB, I'll choose Simulation and then Model Configuration Parameters. Again, the video shows the details of doing that. Selections I make are start time, stop time. I can run this for as long as I want or as short as I want. Here I run it for 60 seconds. I always choose to use a fixed step because if I'm comparing the results of simulations, I always want to have the simulation output given at equal time steps. And I can set up the simulation so each simulation has the same time step. And I do that by picking a fixed step. And I usually pick a millisecond to be the step size, unless for some reason I wish to make it smaller or larger. But in general, I use a millisecond. The integration algorithm I use is, in this case, ODE5. Well, you have a choice of many different algorithms to use. MATLAB in its documentation will give you guidelines as to which algorithms are preferred for certain situations, such as systems or models that have many nonlinearities, or models that have a combination of very slow and very fast dynamics. ODE5 is a good choice, an overall choice for systems like the one we're simulating here. No other choices need to be made, and this is under the choice of solver. Next, if I go to data import export, in this version of MATLAB, I had to limit the data points, eliminate this choice, uncheck this choice to limit data points to last however many values. You don't have to do this in later versions of Simulink, as you will see. In the block diagram, we have some scopes. In the scope block, I can pick this gear here icon, which gives me the scope parameters. And depending on the version of MATLAB, you'll get different choices here. Sometimes you can limit data points to the last however number. Usually you don't want to do that because you want to have all the data points in the simulation. When you bring the output to the workspace, the format we want to save it in is the array. And the default in this version of MATLAB is not that, and so you have to change it. In the latest versions of Simulink, the workspace block needs to be configured slightly differently. And if you're using a later version of MATLAB, I can talk you through that, or you can read the documentation on that. It's very simple, it's just different. So every new version of MATLAB has slightly different ways of doing things, but the things that we do are the same. Process has not changed. Here we see the results of our simulation. This is R position versus time, and this is theta versus time. And we see that the motion occurs about an equilibrium position in the R direction. That's the static equilibrium position. And when R is maximum, theta is minimum. When R is minimum, theta is maximum. And this is as we observe. And it's very distinct, the transference of energy from the R motion to the theta motion and back again. This XY plot is interesting, as this would be the plot, x-axis theta, y-axis R. If you were to attach a laser pointer to the mass and allowed it to trace on a whiteboard its motion, this is what it would show. This is what it would scribe on the board, what the pointer would draw on the board as it goes through its motion. Now, here's my spring pendulum predicted response. This is from the workspace plot. Blue is theta, red is R, one on top of the other. So here you see how the energy gets transferred from one mode to the other. This is with an initial condition of theta 0.021 radians and R0 0.115 meters. This is essentially the same as pulling it straight down. Now, in actual with a physical system, you can't pull it straight down. Even if you could pull it exactly straight down, because of asymmetry in the system, because it's not perfectly symmetrical in terms of the spring, the mass, there will be some slight difference, and that slight difference, that slight asymmetry, will cause it to then go from spring mass motion to pendulum motion and back and forth, and also very distinct transference of energy from one mode to the other. However, in simulation, everything is perfect. So if you pull it straight down with theta being 0, you will get pure spring mass vibration, motion up and down, and there will be no theta motion. So I give it a little displacement in the theta direction, so I will get that, again, transference of energy from one mode to another mode. This plot was created in the MatLab workspace from the two workspace block. Outputs R and theta plotted versus T out. Now, experimentally, on the actual system, I had two sensors mounted. One was a potentiometer at the revolute joint of the spring pendulum, and the other was an ultrasonic sensor mounted at the pivot that rotated with the spring pendulum, but measured the motion in the R direction of the mass, so the in and out motion along the R direction. So as I say here, the plot was created from two sensor outputs, a potentiometer measuring theta, an ultrasonic sensor measuring R. And you can see the similarities between the prediction and the measurements. The transference of energy from one mode to the other is not as clean, is not as distinct. Also, you see that there is some friction in the system, so the amplitudes start to decay slightly for both R and theta. So there are some differences, and also in 60 seconds, we get more than, in this case, 3 cycles in our actual simulations. So here we see a comparison of, on the left, for these initial conditions, simulation, and on the right, experimental measurements. So you see that on the left, I have 1, 2, 3, 4 cycles. On the right, 1, 2, 3 cycles. It's very distinct in terms of going from one mode of motion to another. Here, not as distinct. I still get the theta motion even when the R is at a maximum. Theta doesn't completely go to 0. I also see there is decay in the amplitude because of friction, And in my simulation, since I have not modeled friction, I don't see any decay. So now the question becomes, is my model good enough? The question that I need to answer is, why was I modeling this to begin with? So is the model adequate based on the comparison between predictions and measurements? You have to answer the question, why are you modeling this? Is it just to get insight into the behavior of the system? So I think our model has done its job. If we need it to verify or for some physics investigation, then maybe it is not as accurate as we need it to be. So we ask the question, what attributes in the physical system are missing from your physical model? It could be friction. It could be the fact that the spring has mass and also dissipates energy. It's not just a pure spring. It also might be slightly nonlinear. The mass is not a particle. It's actually a rigid body that changes its orientation. The pivot is not frictionless. So there are several things, several aspects of the model that we could add that make the model more real. So how would you make the physical model more accurate, be a better representation of the actual physical system? You need to answer these questions, but you also need to answer the question, why are you modeling this system? What is the purpose? And that will then tell you how accurate your model needs to be. Let's repeat the spring pendulum dynamic system exercise, but now let's use LabVIEW. Let's remember what LabVIEW is. LabVIEW stands for Laboratory Virtual Instrument Engineering Workbench. It is a system design, prototype, and deploy platform for mechatronic systems. It is a graphical programming language from National Instruments, NI. LabVIEW programs called virtual instruments, or VIs, have front panels and block diagrams. The front panel is the user interface, and the block diagram contains the programming code. LabVIEW is graphical programming for data acquisition, system control, and industrial automation. MatLab, which stands for Matrix Laboratory, is a numerical computing environment developed by the MathWorks. In mechatronics, MATLAB is used for modeling, analysis, and control design for dynamic physical systems. Simulink, which is part of MATLAB, and LabVIEW block diagrams are very similar, and the steps to create block diagrams in either environment are the same. Here is a top 10 list. Top 10 things you should know about LabVIEW. You should read these carefully and refer to them often. Number 10, LabVIEW lives on the right click. So should you. Number 9, know the wire code. It's your duty. Number 8, use LabVIEW project files for all your tasks. Number 7, tack down your function palette. Number 6, know your controls. That is the control key plus a letter to perform various functions. Number 5, messy VIs spell disaster for operator software relationships. Number 4, keep it on the screen, on one screen. Number 3, LabVIEW is a programming language. Garbage in equals garbage out. Number 2, save early, save often, save all. Number 1, Control H is your new best friend. As I said, please review this list carefully and refer to it often. Let's now use LabVIEW to solve the coupled nonlinear ordinary differential equations for the spring pendulum dynamic system. As we see here, the nonlinear equations of motion are written. They are coupled and they are nonlinear. They are ordinary differential equations that cannot be solved analytically. We have already solved these using Simulink. We will now solve them using LabVIEW. The steps that precede the programming in LabVIEW are the same as the steps that precede the programming in Simulink. Step 1, we solve for the highest derivative in each equation. You can see that in the first equation, we have solved for the second derivative of r with respect to time. In the second equation, we have solved for the second derivative of theta with respect to time. Step 2, create two stems. The first stem will integrate theta double dot to give me theta dot with an initial condition on theta dot. Then I will integrate theta dot to get theta with an initial condition on theta. The second stem consists of an integration of r double dot to get r dot with an initial condition on r dot, and a second integration of r dot to get r with an initial condition on r. Step 3, do what the equations say, just as we did in Simulink. I'm using LabVIEW 2017, MyRio. The MyRio stands for Reconfigurable Input-Output. The MyRio is a real-time controller. It's a piece of hardware from National Instruments. This LabVIEW version has functions specific to the MyRio that facilitate real-time computer programming. We will not be using or needing any of those features. Basic LabVIEW is all we need to solve our coupled, nonlinear, ordinary differential equations. I open up LabVIEW 2017. I proceed to the upper left-hand corner to File. I open up File and I choose New Virtual Instrument. Let me just remind you that there is a detailed step-by-step video that takes you through this entire process, one step at a time. As we see, there is a block diagram, and on the block diagram, we create our computer code. This is our graphical programming. On the front panel, we have our user interface. This is where we interact with our program and display all our results. I first open up on my block diagram a control and simulation loop. We're performing a computer simulation. All of our work will be done within this solid boundary that you see. We will set the integration algorithm. We will set the time step for the simulation. And the equations will be solved numerically within this control and simulation loop. In this control and simulation loop, we configure simulation parameters. Here, the simulation parameters we need to focus on are the initial time and the final time. I'll be running my simulation for 60 seconds. I can pick a ordinary differential equation solver, and I choose to pick this one as it is a fixed step solver. I prefer to use fixed steps as it is easy to compare results from different simulations if I have results given at equal time steps. The time step that I choose is 1 millisecond. I usually use this as a time step unless for some numerical reason I need to make it smaller. but I rarely make it larger. This is all we need to change in our configuration, simulation, parameters block. Here is my front panel. On the front panel, I've inserted 4 numerical controls, one for each initial condition for my 4 integrators. The reason I do that is so that I can change the initial conditions on my front panel without having to go back into the block diagram programming to change those values. Any values that we think we might want to change, we should have them represented on the front panel where the user interface is, so that they can be changed from simulation to simulation, or even during a simulation on the fly. When I do that on the front panel, they appear on my block diagram within my control and simulation loop, and you see them here. I then lay out my 4 integrators, and you can see them here. 1, 2, 3, 4. This integrator will take me from theta double dot to theta dot with an initial condition on theta dot, and then from theta dot to theta with an initial condition on theta. These 2 integrators will take me from R double dot to R dot with an initial condition on R dot, and from R dot to R with an initial condition on R. These are my 2 stems, just as we did in Simulink. Once I do this, I then do what the equations tell me to do. What I've done is I've brought in blocks that I know I will need to graphically program the 2 nonlinear coupled ordinary differential equations. A gain block, multiplication, summation, multiplication, raised to a power, constant, division, reciprocal, sine, cosine, as well as 2 waveform charts. When I insert the waveform charts on the block diagram, they then appear on my front panel. One chart will plot R versus time, R on the vertical axis, time on the horizontal axis. The other will plot theta on the vertical axis versus time on the horizontal axis. Then I proceed to do what the equations tell me to do. The best way to determine if your block diagram is correct, consistent with your equations of motion, is to write the equations from the block diagram. There is no reason why the block diagram should ever be in error. It should always be consistent with the equations of motion if you follow this step. The equations of motion might be incorrect, but the block diagram should always be consistent with the equations of motion. Let's do that. This is my theta stem. This is theta double dot. Theta double dot is the product of this line here, which is the reciprocal of the sum of L plus R. This is L, my spring length, which is now a parameter I can set in my front panel. And R is a variable that will change with time that comes from my second stem. This is L plus R. This is 1 over L plus R times the what? Times the sum of minus 2 times the product of this line here is theta dot, and this line here is R dot. Then minus, and I follow this line around, minus 9.81, which is the acceleration due to gravity, times the sine of theta in radians. This is g sine theta. That is my first equation. My second equation says that r double dot, which is this arrow right here, is equal to the sum of 4 terms. And I have a summation block with 4 inputs. The first input is the product of, and the output of this summing block is L plus R. L plus R times, and I follow this line around, and I follow this up to here, and it's the output of the square of theta dot. This is theta dot squared, and I follow this line around, times L plus R with a plus sign, minus the quotient of, and the top line is equal to K, the spring constant, which I now have on the front panel that I can change between simulations or on the fly, K times R, K times R, divided by mass. The mass is also on the front panel, and I can change that between simulations or on the fly. The third input is minus the quotient of the pretension, which is on the front panel and can be changed, and M, which I pick off from, again, the numerical input on the front panel, M. This is Ft over M with a minus sign. The last input is plus, I follow this around, plus G, which is 9.81. It's permissible to put 9.81 into the diagram as it will not change. We don't want to put values in our simulation diagram, as in Simulink, that will change. And we do that, then we input them through numerical control on the front panel. So this is G cosine theta, and theta is in radians. G cosine theta, which I follow around, and it goes in with a plus sign. That then is my second equation. I conclude that the block diagram now represents my 2 coupled nonlinear ordinary differential equations. I will plot theta versus time, and I will plot R versus time, and I will also plot R versus theta, and I will do that on an XY graph. And I plot minus R and theta. And what this plot gives me, as it did in the Simulink diagram, is what I would see if I attached a laser light, a laser pointer, to the spring pendulum mass as it went through its motion. Its simple pendulum motion and its spring mass motion, and its transference from one mode of motion to another. So this then is my complete block diagram. Here is the front panel. The front panel has my initial conditions, which are the same initial conditions I use for the Simulink simulation. I also have the 4 parameters that I could change from simulation to simulation: the spring constant K, the attached mass M, spring length L, pretension F sub T. I show plots of R versus time and theta versus time, and a plot of theta versus R. And this plot, as shown in the Simulink simulations, is a plot that you would see if you attached a laser pointer light to the mass and had it point to a screen, tracing out the motion of the mass as it went through its complicated motion from spring mass to simple pendulum and back again. The results are identical to what we found in our Simulink simulation. As you can see here, I've now reproduced my Simulink simulation results, and we can see they are the same. This is my R versus time, and this is my theta versus time, and this is my XY plot. And we see that they're identical to what we found in LabVIEW.